All right. Hello, everybody. Sorry, I'm not here. It's okay. I know I'm the worst. Okay, mirror math. So we've been doing a lot of those ray diagrams, right? We've been getting a lot of practice and we're doing really well with figuring out how to draw those rules, where they come in, and where that object is going to stand, and how that affects where the image is going to be projected. So I know you know how to do that, but sometimes it's important for us to be able to say, okay, where exactly is that image going to land, right? If I'm trying to make it so that I can project an image to an exact location, I need to be able to calculate where that image is going to go. So our big question is going to be, how do we locate and describe an image in a curved mirror? So method 1 is what you guys are already good at. That's that ray diagram. Method 2, this is when we add some actual numbers and I can get more specific. So this is our big equation, all right? 1 over dO plus 1 over di equals 1 over f. dO, that means distance of the object. So distance of object. All right, so that's where like the physical thing is going. So how far away that object is from the mirror. So it's the distance of the object from the mirror. Then we get 1 over di. So di, I'm sure you can guess it, is the distance of the image. And again, that's from the mirror. All right, so 1 over di, that's how far away the object is from the mirror. Or sorry, 1 over do, how far the object is from the mirror. 1 over di, how far the image is from the mirror. And 1 over f, that is the focal length of the mirror. All right, and that's something that's usually given. So basically, these things are going to happen in a couple of ways. I might give you the focal length and tell you where that object is placed and ask you to figure out where the image is going to go. Or you can figure out where the image is and where the object is, and I might ask you what the focal length of the mirror is. Couple of things to pay attention to. If the distance of the image is positive, right? Positive means that it's going to be in front of the mirror. So if it's in front of the mirror, that means the image is going to be real. That means that the light is actually traveling through it, and it's going to be on the same side of the mirror as the object. All right, so positive means it's happening in front of the mirror, but negative means that that image is formed behind the mirror. So in that case, the image is going to be virtual. So light doesn't actually travel through it, and it's on the opposite side of the mirror as the object. All right, so you have to pay attention, because if you are looking at something and you see that the image is virtual, you know that the image is behind it, you have to be the one to know that that has to be a negative di. All right, so let's try an example then. We have a 5 centimeter candle, and it's placed 40 centimeters away from a converging mirror, means my focal length is positive. And that mirror has a focal length of 18 centimeters. How far away from the image is the mirror? All right, so we are looking for how far away the image is, or di. So let's write out the equation. 1 over do plus 1 over di equals 1 over f. And we're just going to plug in all the values that it gave me. All right, this 5 centimeters, that is not necessary until later. That's how tall the candle is. I don't really care about that yet. All right, so that's my height of the object. Doesn't really matter. Now, it's placed 40 centimeters away. Guess what? That's my distance of the object. That's how far it is from the mirror, so that's do. And it told me the focal length. All right, nice thing. I'm looking for the distance of the image. I don't really have to worry about that negative or not, because I know the distance of the object is in front of the mirror. All right, so it's going to be positive. All right, can the object ever be behind the mirror? No, it's always going to be in front of the mirror, so do is always positive. Di is the only one that can be negative. And a real quick thing, we wrote it over here that f is positive because sometimes f can be negative. Right, think about when you have a convex mirror, like that big sphere. That's when that focal length is behind it, right? So the focal length can be negative, like a convex mirror. All right, so this one, Great, F is positive because it's a converging mirror. It's a concave mirror. So I can just plug everything straight in. 1 over 40 plus 1 over di equals 1 over 18. All right, so sometimes with this one, I think it's just more helpful to work with the inverses. So I'm going to subtract that 1 over 40 from the other side. So this is basically di to the negative 1 equals 18 to the negative 1 minus 40 to the negative 1. All right, so when we do 40 to the negative 1 minus 18 to the negative 1, and then don't forget that we have to flip it one more time, di turns out is going to be negative 32.3. All right, so, oh, sorry, I did it backwards. Oh my gosh. See, and now you might be asking yourself, Mr. Schiller, why don't you just restart the recording? It's literally just a recording. And I would say no, because then I have to redo everything all over again. That's so much work. All right, it's positive. I'm sorry I lied to you. Centimeters. So great, there's my distance of the image. It's a positive 32.3 centimeters. So guess what? It is a real image in front of the mirror. Neat. Okay, next thing we can do with the mirror math, right? When we draw those ray diagrams, you can also figure out, hey, is this thing bigger, smaller, or the same size? Did it get magnified at all? We have a magnification equation also. All right, so here's that magnification one. The magnification is equal to HI over HO. That's the height of the image. All right, so how tall my image appears and the height of the object, the actual height of the object. All right, or we can also say it equals negative, be careful, negative DI over DO, distance of image divided by distance of the object. All right, so a lot of times this will just get like combined in one equation. You can say M equals HI over HO, or M equals negative DI over DO. Or if you've seen Sleeping Beauty, you know, hi ho, the song. So they go hi ho, die do. Okay, now that's just a fun little way to remember that there. Okay, hi ho equals negative die do. Amazing. All right. So that's another helpful relationship because it doesn't always give you the magnification. So sometimes you want to combine them together. I would write that down because I guarantee it's going to help make your life a little easier later. All right, some quick things about magnification. Hey, if magnification is bigger than 1, that means that it got larger, right? It's a bigger magnification. If magnification equals 1, it's the same size. And if it's less than 1, it got smaller. This is important. If my magnification is negative, that means that the image got inverted. All right, so this one number can tell us a lot of things. So let's look at our example now. For that same question from above, determine the height and orientation of the image. So I am looking for, sorry, not DI. I'm looking for HI, the height of the image. So now, here's what I can do, and here's what I'm saying. It didn't give us the magnification. I can't use that. I have to use my equation where I combine them together. Hi-ho, di-do. All right, so DI we got from above was 32.3. So negative 32.3 divided by the distance of the object, which from above was 40 centimeters. So over 40 is going to equal hi-ho. I'm looking for height of the image, and it told me in the question above the height of the object was 5 centimeters. All right, so a little cross multiplication. You can do it like this. This is how I like to do these questions. So 40 HI is equal to 32.3 times 5, negative 163.6. All right, divide that thing by 40, and the height of my image is going to be negative 4.1 centimeters. All right, so hey, check it out. My height of the image is negative. That means it's inverted. I can tell the original, the height of the object was equal to 5 centimeters. So this thing is smaller. All right, so my image is smaller. It is upside down. Or in this case, that means I have a magnification that is negative, and my magnification is less than 1 because it's smaller. All right, so there you go. That's everything you need to know about the mirror math for these equations. So now you're going to go ahead and try this out a little bit on your own for a bunch of different scenarios. Remember, watch out for the positive and negative sign, okay? If it's behind the mirror, it's negative. You have to be careful with that. And watch out for this negative in here. A lot of people tend to forget it. All right, good luck, and I will see you later.